Hello, everyone. Welcome to this webinar. Title is Introduction to tsunAImi, Accelerating AI Inference. This is a result of a partnership between CMC Microsystems and Untether AI to provide researchers in Canada with leading-edge accelerator technology from Untether. I am your host. My name is Yasin Hariri. I am a senior scientist, AI and ML at CMC Microsystems. And I have the pleasure to welcome our guest speaker today, Gaurav Singh, Director of Technical Marketing at Untether AI. So today we will cover these topics. First of all, Gaurav will dive into details on the machine learning framework that will support this accelerator card. This includes graph ingestion, calibration, and quantization. How to add and customize layer or operation, quantization-aware training, and he will be also covering custom kernel writing and lowering, including utilizing the image in CLI for network compilation. Creating custom kernels, leveraging tile flow for HPC and kernel testing, incorporating directives into the compiler, and integrating custom kernel into the compilation flow. So all these different components are essential to get started with the tsunAImi accelerator card. So CMC Microsystems integrated this card into a high-end server, which is online today, and it is accessible by Canadian researchers. So we will conclude this webinar with a quick demo showing tsunAImi in action and providing early detail access on early access details, including live demonstration and the different resources that we put in place for people to get started with this technology. So Gaurav, I will stop sharing my screen and I will allow you to start your presentation.
Okay, thank you. So, hello everyone, my name is Gaurav and I'm representing Untether AI. And let me show my presentation. So I hope you can see it. Looks good? Yeah?
Yes, it looks good.
Okay.
Just a note that the webinar will be recorded, and
Okay.
as you see, you are muted right now. We will be taking questions at the end of the presentation. So this is where your microphone and camera will be enabled. Thank you.
Okay, sounds good. So we did a presentation back in May where we introduced Untether AI, and I don't know how many of you were there, but we just have a quick slides on just a refresher on who Untether AI are. So we are a 5-year-old company based in Toronto, Canada, and we help companies execute AI workloads. We run neural networks faster, consume less power, cost less, and so on. These are all investors, 150 employees, 170 million raised. We have these products right now in the market which you can get access to. And then we have a future generation of product which we will talk about in subsequent sessions, but these are the ones which we have available right now. So we have Run AI 200, the chip, which has 500 TOPS, 50 watts power, and then we have TSN 200. So what TSN 200 is that we put Run AI 200 chip on a board, on a PCI board. And that is what CMC has. So CMC has access to the server TSN 200. And then if you put 4 of them together, 4 of Run AI 200 on a single PCI board, it becomes 2 petaops. It's called tsunAImi 800. So the number 200 is coming from 200 megabytes of SRAM, which is on each chip. So TSN 200 has 200 megabytes of SRAM, TSN 800 megabytes of SRAM. This is the industry's first at-memory computation engine. We are at memory because we plug data directly to the computing elements. In our original webinar a couple of months back, we talked about how von Neumann architecture is like very energy intensive because there's a lot of energy which gets lost in data movement, and we are trying to minimize that. And it runs on INT8 Inference, 75 watt total power, but 50 watt is typical. 204 megabyte SRAM, scalable voltage frequency, eco and sports mode. So eco mode means you want to consume the least power. Sport mode means you want to maximize the performance. You want to run the fastest possible. It has 18.4 billion transistors, 16 nanometer TSMC technology, and PCI Gen 4 times 16 interconnect. And then TSN 800 is 300 watt TDP, 1 petabyte, eco and sport mode. Similar stuff, it just everything is 4 times bigger. And then tsunAImi 200, which CMC has 500 tops, 75 watts. It's a smaller form factor. Some of our customers wanted a smaller form factor powered by PCI Edge connector. And it's a good engineering sample which is available to ship today, and you can get access to it through a CMC, or you can reach out to us directly also if you want to purchase one. And it's scalable. The solution goes from run AI chips to like server grade architecture where you can put a bunch of them together in a server. And then this is the core topic for today, which is the imAIgine software development kit. So I'm assuming, and correct me if I'm wrong, but a lot of you are like machine learning researchers, and what you do is that you train a lot of neural networks and then you want to deploy them. And most likely you train in one of these frameworks, either TensorFlow or PyTorch or Onyx. So what our imAIgine software development kit does is that it takes these models, so something which you are trained on like NVIDIA GPUs, let's say, or AWS instances. So you train those models in TensorFlow, PyTorch, or Onyx. It will be in floating point 32 format. As I mentioned, we use integer 8 format, so there is going to be all of that quantization and calibration that needs to happen. So we provide the imAIgine compiler and imAIgine toolkit. So we take that graph, which is floating point 32, convert into integer 8, and that is what we mean by graph lowering. And then we have a physical allocation toolkit and simulation feedback. So how would it perform? How much power would it consume before you even put it on the board? And lastly, the runtime, which takes the converted model from your floating point 32 model to integer 8 model. It takes that model and then prepares an ELF file, which is used to run on our hardware. All the right knobs exposed. You can do a lot of things. Very push button, ready to inference, and a lot of people assume that because you go from floating point 32 to integer 8, we would lose some sort of accuracy. We have a lot of tools which allows you to maintain that accuracy. Like if you do out of box, you lose some accuracy, but if we allow us to do like quantization-aware retraining or other calibration, we can get back that accuracy which you saw in NVIDIA. So what is happening is that you got a quantized model which has the same accuracy, it runs faster than NVIDIA, and it consumes less power. That is what we are looking for. This is the standard tool flow. So we start from this customer, your pre-trained model. This is what you have already. So keep in mind that we are an inference service provider, inference software provider, and inference hardware provider. We are not designed for training. So you will continue doing the training in their models, and training takes a lot of time. Like you had to figure out the product requirements, the accuracy, the latency requirements, and so on. And then there's a lot of like hand tuning involved, so fine tuning. So all of that you take care in NVIDIA, AWS, and so on. And then you come back to us, you come up with the model. And we also have some model in UAI model part, and UAI means Untether AI. So we already have a few models. But if you want to bring your own model, you are welcome to bring your own model too. It should be in one of these formats, which is TensorFlow, PyTorch, and Onyx. There's a quantization framework. After quantization, it prepares an ELF file which gets compiled. After quantization, it generates a PB file. So remember, TensorFlow has this protobuf file as an output. Quantization, we convert that floating point protobuf to integer 8 protobuf. It is still a protobuf file, but it's a different protobuf. And then compiler converts into an ELF file which gets onto the runtime. Physical allocation is basically if we have a neural network which is not fitting onto the chip, like if it's a large neural network, or if you're looking for a specific mode where you want to like minimize the power, or want to be somewhere in between. So I talked about eco and sport mode. So eco is like least power, Sport has like maximum performance, and you want to be somewhere in between. You probably want a little bit more power. You're okay with a little bit more power, but you want like more performance. So you can actually physically allocate which part of the graph goes on which banks. And we have 512 banks. So if you look here, you can physically place each of the nodes on the graph. And that is an option. Or you can just choose the standard way. So we have a automatic allocation, but it's modifiable. And then we have some simulation tools which are like cycle accurate. It allows you to do all sort of analysis and visualization. You can figure out which bank is congested. And by congestion, I mean they are looking for data, they're ready to take on, but they are waiting for something else like a bottleneck. And lastly, the runtime, which has like health monitoring software. It gives you all sort of information, like for example, how fast the neural network is running, temperature, etc. So this is the quantization framework. We start with a train graph, which is a protobuf file in floating point 32. We have these framework optimization, which is quantization, AdaQuant, and quantization-aware retraining, also called QAT, where we add quantization noise also. So when we convert a model from floating point to integer, there is some quantization noise which gets introduced, and that least reduces the accuracy. So if we train the model while allowing that quantization noise to also be part of it, it improves the accuracy backs. So it goes from one protobuf file to another protobuf file. Eco mode and sport mode, so you're looking for efficiency, you fit in the smallest area or least power, or you go for performance, which is like, I don't care about how much banks it takes, I want the fastest performance. So these are the compiler optimization options. Let's talk about how other options we can. So for example, we can do pipelining the whole neural network like fit like sequentially. For example, let's say if your Yukon 2D is too big and it's taking a lot of banks and you don't like it, or maybe it's a bottleneck. So usually what happens is that your bottleneck layer is the maximum speed your neural network can run on. So for example, if this Yukon 2D is running at 10 FPS and everything else runs at like 100 FPS, your neural network will run at 10 FPS. But what you can do is that you can split this 10 FPS neural network, neural layer, and split into 2 or 3 or 4, whatever way you want. And this 10 FPS becomes 20 FPS, and now your neural network is running at 20 FPS. So you can do layer application, you can do subgraph application, you can even do multi-instances. So you can just have multiple instances of the same neural network. Instead of running one neural network, I'm running 3 copies of the same neural network. So all of this is option which is available to you. And then obviously we talk about runtime, which is a high level API. It has C++ API and a Python API. The C++ API is the low level API where you can access to various parts of the chip. So it's a slightly steeper learning curve, but it gives you more flexibility and more customization. Then we have system management and debugging tools and health monitoring. So that is on the slide portion, and we wanted to make it like heavy. Sorry, so we wanted to make heavy on demo part. And let me go back to this one and let me share something else. So before I go into the demo part and live training and all, I wanted to show you where all the materials are coming from. So let me share my screen again with a different set. And what you're looking at is our customer support portal. So on the right, you have Yasin has access to it, and I'm sure we can make it available to other people based on their needs. Or maybe Yasin has a way to make it available. So the documentation portal contains all the information you would need to run your own neural network. So first you will start with something like getting started. Let me input my credentials here. So there's the hardware installation guide. There's SDK installer for RHEL and Ubuntu, runtime installer for Ubuntu and RHEL. You can do a pre-built Docker container if you just want to run the demos, or you can build your own Docker using Docker scripts. Then we have some customer demos under for examples. You install all of that. I'm not going to walk you through the installation process because it will take some time, maybe 5 to 10 minutes, and I don't want to waste that. Um, but this is where you will get all of that information. Now, let's go to the tutorials and demos which I'll be running through. So if you go on the left, there's a big navigation bar and you find tutorials and demos. You click on tutorials and all of the tutorials which you would need. So these are like notebook tutorials, and I know you guys use a lot of like Jupyter notebooks. So we have made tutorials based on Jupyter notebooks. So you can start with working in TensorFlow, getting started with runtime, model ingestion, quantization-aware training, advanced quantization, calibration, threshold tuning, fixing bank allocator, detecting performance degradation, SSD, YOLO, YOLACT, multi-chip, and so on. So as you can see, we have a lot of tutorials, and there's no way we can cover all of that in 1 hour. But here is where you will get all of that. And then second thing I wanted to talk about is the kernel development guide. So for example, let's say you have a model and you don't find the right kernels, you are not able to get the kernels which we have supported. Well, you can come to this guide, which is the kernel development guide, which all talks all about is how to map kernels to hardware. So we talk about like machine learning concepts, we talk about our hardware architecture, and basically kernel is the mapping from layer to hardware. We can have, so if you have convolution 2D layers, it's the same thing on NVIDIA GPUs, it's the same thing on Untether AI, but the kernels will be very different. The kernels are written in CUDA in NVIDIA, in our case it's written in a different format. So how do you design all these kernel design considerations? These are the SRAM constraints. So for example, you have only 204 megabyte, and each bank has 512 processing elements, and each processing element has 200 kilobyte memory. So all of that, our KDF format, which is kernel data format, Axon framework, UDF examples, style flow. I wanted to show this because it's hard to cover all of that in 1 hour, but once you need more data on this, you'll go on this website and find all of it right here. So we have kernel API, kernel debugging, class, tensor stream, and so on. So all of that can be found in this website. This website is called support.untether.ai. support.untether.ai. But the access is restricted to people who have either purchased our systems or acquired our systems. So like CMC has access to the system, but we can arrange access to it based on the needs of the people who are interested. And then we have also inference applications and tools. So all of that information is here. Good thing about this software portal is that you can go through different versions. So if you have been a customer for us in, let's say, September of last year, so you're probably using 2209. We release a software new version every 3 months, and sometimes we do a minor release also. So like a month later, we make some bug fixes or add some more features and enhancements. So all of this information. So for example, if you signed up in 2303, you can go back and just use that documentation. But if my recommendation is always use the latest documentation. And the cool part is the searchability. So let's say I don't know where is ULACT tutorial. ULACT is semantic segmentation network, which I want to run through. So I'll just look up ULACT here, and it should tell me all the results, and there we have it. So it's ULACT real-time instance segmentation. So it's very searchable. All of that is covered. It's a plethora of information. One other cool thing, so we found out that a lot of our customers are working in data centers which have like limited internet access. So you can actually go to this reference, click on available documentation, and you can download all of this information into PDF. So once you lose the connection, it's fine. You already have the information in form of PDF. So that is something which some of our customers have found useful. Okay, so this is all about where the material is coming from, and let's go through the material itself. And let me come back to this. And I'll try to reshare this time. Okay, so I already mentioned how the whole process works. And I have a few tutorials which I'm planning to walk for about next 37 minutes or so, and then we can take some questions. If I'm not able to answer your question, maybe they're more technical than you're looking for, maybe you're looking for more deeper answers, I can take those questions and back to my engineering team and we can come back with those answers. But the first thing first is that how do we get started with the Untether ML library? So on Run AI 200, we have an Untether ML, Untether machine learning API. It's built on top of TensorFlow. So we have a tutorial where we walk through all of this. So let's go through this. Let's start with um, MNIST tutorial. So I know it's very basic, but we just wanted to show how our Untether AI model works. So essentially you start with importing NumPy, TensorFlow, Untether ML. You load the MNIST data, get, train, and test. Now you'll have to resize them because these images are like length in sequences. So you'll have to make them into reshape into 2024. And next we rebuild the model. So far we haven't used any of the Untether ML. This is like regular TensorFlow and regular Keras. So we start with the model, we start with the ReLU activation, dense layer, 256, 64, 10, coordinate MNIST. Nothing of Untether ML has happened. Now what we are trying to do is that we are trying to figure out how does the original model do, because we want to compare it with Untether ML model. So it has 279,000 parameters. All of them are trainable. Let's see how it does. So we run it on validation data. It's pretty good accuracy. Looks good. Let's get the accuracy. So our original model, the TensorFlow model, which came from the Keras directory, on itself is giving us 97.67% accuracy. Now we need to keep this in mind because we have to come back and compare this with Untether machine learning libraries. So what we do is that we take this model, which is, we called it original model, which is a TensorFlow or Keras model. We have this API call called uModel from model, original model. So we start with a floating point model, we convert into uModel. And this is where you have a uModel class. U stands for Untether here, so in case you're curious. So what uModel has done is that it can switch run modes now. So you can do regular model accuracy, on-chip accuracy. We have a way to convert this floating point into integer 8, and we can fine tune. So all of this is allowed in this uModel class. We are calling a layer caller, which is a standard caller, and we are comparing uModel accuracy out of box. We are not doing any quantization, we are not doing any calibration. We are doing quantization for sure because we converted, but we are not doing any retraining or something. So uModel accuracy itself is 0.9767, so similar accuracy. Now run AI 200 coprocessor performs all the computation in limited precision integers, which is integer 8. So we do need to do some sort of calibration and quantization here. What does quantization usually mean is that you find out the representative subset, like take a subset, see the maximum and minimum range, and then you scale them up at the basic minimum. And that is what we are trying to do. So what we need to do is that we need to take some of the training data, let's say first 100 examples, and we call them calibration set. So that will be used for calibration. And then we use the remaining, like less than whatever the number was, we take the 100 out of it and we train on the remaining subset of the data. Why did we separate calibrate and why calibrate? Because that will be using for our quantization tool. Quantizer, you have like multiple options to do that, but we'll just call the default quantizer for now. And we have all the information needed on what all the quantization options are based on our API. And it's a simple quantizer. You call the default quantizer and you quantize. And for quantization, you give the model name and you give it the calibration data. So fairly simple, took nothing, very less time. And now we'll use a U-image classification model where we will take the original model and we'll take the calibration data and we'll use a classifier. Now we should simulate on-chip accuracy. So now we have a U model which gives us an accuracy, but we need to know how will it do on our chip. So we have something called Untether caller, which is a layer caller again. This will indicate the expected on-chip accuracy of the deployed model. And we compare the accuracy of Untether. Fairly simple, get the layer caller, call the accuracy. And estimated on-chip accuracy is 0.977. So this is on-chip accuracies. Remember the previous accuracy was 0.9767. This is 0.977, so slightly better. And then we run the next cell. We got the standard accuracy. We got the layer caller. The single caller that we assigned got broadcast to all layers, and it has reset the layer caller. So it's all good. Now, in this case, we don't need to fine-tune a model because simple neural network, we're already doing very well, and our accuracy is better than what we saw in the other case, in the original model. But this will not always be the case. The complex the model is, for example, say Resonant 50 or YOLACT or YOLO XL, in that case, there is expected quantization accuracy loss. So how do we regain some of the accuracy lost during the quantization process? So one strategy is to train a model which is optimized for quantized accuracy, and we can do that by introducing quantization noise. And what quantization noise is that? Basically, when you quantize, there's like artifacts which get introduced, and these are, I would say, they call them distortions, and that needed to be added. So for example, if you want to prepare your model for the quantization noise, you show the model that these are the quantization noise you should be expecting. So we add that noise during the training process. It's usually slower than regular training, so we don't recommend doing a lot of like quantization-aware training. What we do is that you go through the U model conversion and fine-tune with a very small subset of data. So it's a method to fine-tune an already tuned network rather than applying quantization-aware training to train a network from scratch. So never train a network from scratch, train it on NVIDIA and fine-tune using quantization-aware retraining. So this is a QAT, which is the quantization-aware training. What we are looking for is categorical cross-entropy loss, which is what we use standard. We are using optimizer for Adam. And that's it. You model compile, you model fit. Very standard API calls. And then we quantize. And let's see, on-chip accuracy after quantization of our training is even better. So we started with 0.977, now we're at 0.9804. So it actually improved the model beyond the original accuracy. This is not guaranteed to work for like every model, but it usually works even with like bigger models. Now what we'll do is that we'll take this model and write a protobuf file. So let's call it getting started.protobuf file. You can visually inspect. So I don't know if you use Netron. You can use the UModel protobuf visualizer or any other tool. Netron is a tool where you put Onyx files or any protobuf files, and it visualizes like what layers are there, what are the input shapes and output shapes, and so on. So you can actually visualize this U model also. So it's nothing special there, as in like we're not trying to hide anything. You can actually visualize it. Now this process, when you write this getting started.pb file, it generates a protobuf file, which is quantized integer 8. It also generates a U model file, .u model file. So it will have getting started .u model, .pb.u model. Why do we generate two files is that in case you want to change something. So for example, you get some new data, you want to retrain, or you want to do a quantization-aware retraining with a different calibration data set and so on. So you can actually take that U model, retrain all of that, and then you can write PB again. So you can do this getting started.pb.u model. Then from U model, you can convert into reloaded U model. And the last process, so this is all, you had got a ELF file, you got a PB file. Sorry, you got a PB file, not ELF file. But ELF file is needed to run it on our hardware. And this is the process. So you do imagine compile and take the converted PB file. And that's it. It will generate an ELF file which can be loaded on runtime. And I can show you how it's done on runtime too. But let's stick to the ML framework part. So this is done and it will generate a compile file. Now, some of our customers are, they are curious about how the compilation happens. So usually compilation happens in 3 steps. And I have a way to demonstrate that. So this is our regular compiler. It takes a UI model PB file. It goes through model compiler, which will generate bank graph, which is a UGF file, and params, which is a NumPy file. Then bank allocator, which will allocate which layer goes to which bank and so on. And that will generate allocated bank graph file, HTML file, and full config file. And lastly, that all of this goes to bank compiler, which generates an ELF file and DMA hooks.json file. All of that is needed for running on runtime. So sometimes people want to understand the intermediate files also. In case you are curious, instead of doing like imagine compile, you can do something called imagine compile stage, compile underscore stage, model compiler. So you imagine compile underscore stage and then you call this stage. This will generate the intermediate files here, which is input.bg.ugf and parameters. Then you'll pass all of this information into bank allocator. So imagine compile stage bank allocator. You provide the UGF file, allocated graph. This will generate a bunch of things. So this will look something like this. And then lastly, you will have compile stage bank compiler. You'll provide allocated graph, params, and app.elf. And this will generate the final ELF file. So SRAM utilization is 2 megabyte, SRAM utilization 1.2%. So what I have shown you right now is that you can take a Keras model or a TensorFlow model directly, and then you convert them into U model. Then you do quantization or calibration based on the data set you have. It generates another protobuf file, and then you do imagine compile to convert that protobuf file into ELF file, and that goes on to runtime. Now, let me show you some other ways to do ingestion. So I just showed you like Keras, but you probably are using like PyTorch or let's say Onyxes. So I have another ingestion tutorial where we walk through some of those. So let me install TensorFlow, Torch Vision. We will use the same model, MobileNet 1. MobileNet, I think V2 probably. And what we will do is that we will take MobileNet from 3 different sources. So we'll take TensorFlow Hub, we'll take PyTorch, and we'll take Onyx Hub, all pre-trained models, and we'll try to convert them into U models and run them and compile them. So the first step is using TF model. So we went to this website called tfhub.dev.google imagine MobileNet, downloaded MobileNet from there. For PyTorch, we will do this, which is torch.torchhub.mobilenetv2.eval. So we got torch model. Then Onyx, if you use Onyx, we can do Onyx Hub also. You can download this model from them. We'll use the same input for all of them. We provided this input data, which is just random numbers from batch size and shape. How will I convert TF model? So U model from model, TF model, and it becomes, it should give me an error. And what is happening is that contains unsupported pre and post processing nodes. So what it means is that MobileNet is something which we don't have right now. So for example, if you are using MobileNet model and we don't have all the layers or kernels needed to increase that. Now you had two options. And why would it happen? So for example, a lot of companies have like custom layers. They build their own layers and they build their own kernels. Sometimes they have custom ops, which they don't want to share with us, or they don't want to share with the API. Similarly, NMS, non-max suppression, it's a non-linear operation. So that conversion takes a lot of time, and we recommend that you use Untether version of NMS. So like a lot of non-linears have Untether version of NMS, and we don't recommend converting from TensorFlow, PyTorch, or Onyx into Untether version. Rather, you subgraph it. By subgraphing, I mean you remove that part which is not supported in our SDK as it is, and you take from our SDK. So like for the case of NMS, ignore the NMS which you got from the pre-trained model, subgraph it, cut the NMS part, and then add our Untether optimized NMS. So we do it much better than the other people, and it's designed for our hardware. So this is expected to give us an error. And I'm just showing you Torch model and then Onyx model. So all of these should be, these are not supported. So what does subgraphing mean here? We refer to the practice of removing portion of the graph with unsupported nodes as subgraphing. And as I said, NMS implementation is more complicated. So you may want to introduce either support for that layer, either you write your own kernel, which you can go through on our website, or you can do a subgraphing. You can remove that part and attach our implementation. So how would you do subgraphing? So first of all, you convert the model into a TensorFlow graph def, which can be written into PB file and that can be examined in Netron. So we have written this TensorFlow model into PB file, which can be observed in Netron. What Netron does is that it gives you layer names. So for example, I know that right now this visualization doesn't work in this cell, but usually what it does is that it tells me layer name like con2d, and its name is like mul and con2d and con2d like c11 and so on. So what it's asking us to do is that we take this part and we take subgraph out of it. So we remove that part of the graph which we don't want. And for Onyx subgraph, you take the full U model from Onyx layers and some similar things. So you break down at input and 627. 627 is the layer name, which I cannot show you right now because this thing is broken here. But basically 627 is the layer name. Similarly for PyTorch, you can do all sort of subgraph. Now for inference, you call the standard caller like last tutorial. Standard call for both Onyx model or then Torch model or TensorFlow. And then you print the TF output shape. Now you'll see that the output has like 1001 classes because one class is usually for background class. So it's 1,000 class neural network. What we have shown in this tutorial is that you can take a pre-trained model from TensorFlow, PyTorch, and Onyx, and try to ingest it. In a lot of cases, it will ingest on its own. So all of the layers will be mapped to untether layers and kernels. If it doesn't, it will give an error, which I showed you that it's giving an error here, that we don't have the optimized version for it. Like it's not a direct conversion possible. Now what options you have is that you write your own kernels, which is not difficult. You can just go to this here, kernel library, catalog or kernel development guide, I should say, and you have all the data you need. So for example, what are the kernels available we have? So convolution theory kernels, we have these kernels. So 64 by 256, 256 by 64, 256 by 128, and so on. So if you see something which is not here, you can go back to the kernel development guide, go through the process, and just write the kernels here. So you can do that, or you can stick it out. So in the case of, let's say you are doing object detection, most object detection have NMS layers. NMS layers is a non-linear operation. It's not optimal for our hardware, but we have written a new version of NMS, which you can just take it from our SDK. So remove the subgraph, remove the NMS, and then attach our NMS tool there. So that is the ingestion part.
Gaurav?
Yeah.
Yeah, just a question. Is there a way to automate the subgraphing?
Um, you will need to know which graph you want to remove, right? So for example, you found that the error is coming on at this particular layer. Then you'll need to specify that layer name that you want to remove. And in some cases, we have direct ingestion, but we recommend that, for example, certain batch norm layers, you can actually convert them directly into our model. But we recommend that you take that out and use Untether version because it's optimized for our hardware.
So my understanding is that when you ingest the graph and you encounter parts of the graph that are not supported by Untether SDK, you have to identify them, then look for the corresponding optimized version from Untether, right?
Right. Yes. Or if we don't have, you'll have to write your own kernel, which we are happy to help, but we also have all the guides on our website.
Okay, thank you.
Yeah.
For the attendees, if you have, because this is a lot of materials and I enjoyed the live demo, if you have any actual question, you can raise your hand and ask it, because I see the demo part is very long. Thank you.
Yeah. I think you should just speak up because I cannot see you at all. So I'm just looking at my screen right now, and I don't know if someone is asking questions. So Yasin, thank you for speaking up when you had a
Yeah,
question.
I will monitor the question. No worry. Thank you.
Okay. So let's talk about ULAC tutorial. This is people love MNES because it gives you some examples on like how to actually what are the standard callers, how do you get a model like from your model. But let's talk about some real neural networks which people are using and deploying and our customers are deploying. In fact, ULACT is actually a model garden network or model. Some people call it model zoo. We call it model garden here. So ULACT you can just use out of box here in our Untether devices. So when you buy an Untether device, you'll get ResNet 50, you'll get ULACT, YOLOXL, and some other neural networks which comes with it. Now, what ULACT is a real-time instance segmentation. It classifies and also makes bounding boxes, but it also does object boundaries. So like each pixel is classified as belonging to a certain class. So this is a visualization of ULACT. Now, our version of ULACT, which is implemented on Untether hardware directly, utilizes ResNet 50 backbone. So usually object detection and segmentation networks have a classification layer, and then there are like region proposal networks, field proposal networks, RCNNs, and so on. This one is based on ResNet 50 backbone. We achieve a mean absolute precision of 29.9 and segmentation of 27.9 on an image size of 550 by 500. Now you would ask, what if my image is not 550 or 500? We do support different image sizes. So for example, you can do 200 by 200, 300 by 300, 750 by 750, and 1000 by 1000. Unfortunately or fortunately, we have optimized this 550 by 550. But if you want to use a different size, you'll have to do a full retraining of the original model. But if you're happy with this size, you can just use it as it is. So it's a single stage object detection model like YOLO V3, but it has a mask generation branch that leverages the existing detection features without feature localization. So I'm not going to go into like semantic segmentation details, but it uses a feature pyramid network, which you're probably familiar with, and perform detection of various sizes. Like most object detection and segmentation network, we have non-max suppression here. And if you actually look into the source code of ULACT, or if you open this tutorial, or you'll get the source code if you get SDK, you will see the Untether version of NMS, and which is slightly different than the CUDA popular version of NMS. And we have done it to work well on our hardware. It runs way faster than other NMS algorithms. So it has three branches, one for detection, classification, and mask coefficients. What you need to do to run through this demo is that you need COCO validation dataset and COCO annotation dataset. So let's do that. This is my workspace tutorial notebooks, datasets, COCO. I am going to run through some OpenCV Python installation, and I'm going to load this model. So Onyx path is coming through from the model zoo. So Untether.ml also has this public zoo, which is also internally known as zoo. If you click on zoo, it gives you several options. So like less than 50 is one, ULECT 7 one, ULECT 550. So in this case, we call ULECT 550 because it's already included. It gives us an Onyx. We load that Onyx file, and I think I already ran this. Now we have to remove post-processing and redundant layers. So we have a redundant ReLU layer in the original ULACT model, and it has like transpose, reshape, and concatenation layer. And we feel that these are redundant because they don't do anything, and we remove those layers, or else the model cannot be compiled properly. So what we need to do is that we need to use Netron, as I talked about. So I don't know, have you guys heard of Netron? I'll just show you here. So basically you can add any Onyx file and it visualizes. Let's see if I have an Onyx file here. Oh, I wish I had an Onyx file. No, I don't have an Onyx file, but let me get an Onyx file. Let's see if they have Onyx file here. Okay. Anyway, so I cannot find it right now, but Onyx basically you can upload it here in Netron. It shows you the layer by layer on what exactly is going on there. So you can see Netron visualization of FPN, proton head, and prediction head. So why do we need that? We need to know the names of these transpose layers, reshape, and concatenation layer, which we need to remove. And that is where the subgraphing part is. So we are defining input here, prototype output, box outputs, score outputs, and mask outputs. Standard stuff, test.pb, GauTF, and so on. Then there's a redundant ReLU operation, which occurs in the output of bilinear interpolation layer. Unfortunately, none of these images are working. So they were working before, but now I can't show you. So these are actually screenshots of Netron visualization. But it's similar to what the subgraphing thing we have done before. So we are just removing the layers. You will notice that we don't, if you go onto our website and support portal and look for like layers and kernels we are supporting, you won't see ReLU there or even batch normalization there because we include them in the layer above them. So like after a convolution layer, there's a batch norm layer, right? So we fuse them together. So we have ReLUs we have batch norms and all, but it's fused with the previous layers. So we remove these nodes, which is the ReLU and the nodes here. So for example, in this case, the ReLU node name was ReLU 160. We remove that node, and then we optimize the graph and then fuse it. There's a lot of technical details on like RGB and BGR format. How do you quantize the normalization parameters for like sigma and So like 0 to 55, these are the standard deviation and variances, which you will need to know when you quantize and calibrate. But in this case, we just take it from the paper itself and implement it. Now we have already removed NMS here. We can Now we need to attach our NMS API, which is the Untether AI NMS. We can only do that using prediction head detection classification. And for that, we'll call NMS AKI. So this is the u.attach NMS subgraph. You attach the graph definition, which we already like subgraph. So we have cut it down. This is the remaining graph. We attach the NMS subgraph here with all these parameters, so like scale and object inclusion, number of classes, and so on. I know I'm going very fast here, but we have to cover a lot of things. And as I said, you can download all of this from our website right there. So we explicitly set the flag return IDs equal to true in this is here. And we do that because the 8th channel of the last dimension will possess a unique ID for each detection. So that unique IDs will be used to retrieve the correct mask coefficients that is needed here. We are not just doing the object detection, we are also doing object segmentation. So per pixel knowledge is important here. And we run this part, which is we build post-processing graph now. So remember we removed the post-processing. Now we have to attach that. And then we attach everything and we'll create our U model. So now we already have a model. We have a stitched graph, which is the stripped out version. We removed all the stuff. We added a graph and then mapping. And mapping includes just the NMS layers. Now we'll do quantization, U model from graph definition. And we are doing that, while waiting for that. And then we have a calibration size and validation size. So we take 10 image data set and for calibration, 10 for validation. And let's calibrate it. So index has been created. This is just for visualization, which is TQDM where you're quantizing. So it's going to show your progress bar that's calibrating right now. I'm waiting for it to run. Let's evaluate the model. So this code is basically you're looking for data set, it's looking for the model, and you're looking for validation size. And it compares the outputs to the validation size and it gives you a mean absolute precision. So in segmentation and detection, we use mean absolute precision as matrix and not accuracy. And we call Untether caller and it will print the detection mean absolute precision and segmentation mean absolute precision here. And this will take some time because this is a huge model. It's running at 13 seconds per image so right now.
So this is running on a similar card, right?
Yes. So this model right
it's one
now
chip.
It's a 4-chip card actually.
4-chip, okay.
Yeah.
And there is a way to specify the number of chip you want to use for each application, right?
Right. You can specify the number of chips. So for example, if you have a 4-chip card, you can specify I want to use 1 chips or 2 chips.
Yeah.
And it does that. So you can provide the information in the config file. And then once we are happy with, so we are looking at 24.49 and 24.57 mean absolute precision. The original paper which came from NVIDIA had 29 of these numbers. So like instead of 29, we had 24 and a half. But we haven't done any quantization-aware retraining. So we can do that if you want to. But right now we just take the model, convert into protobuf file in integer 8. And to get it ready for runtime, which is to imagine compile, you'll add .pb. And it should generate an ELF file. And let me show you something else. So the only thing which we haven't covered so far is we have gone from floating point protobuf file to integer 8 protobuf file, did quantization, resaved them, and then did imagine compile. What we haven't done is that we haven't done runtime, which is take the ELF file, which is the output of a compile step, and then so in this case we will go through that runtime process, and we will just repeat what we talked about the first MNest tutorial which I walked through. Exactly same thing. Let's get the data from MNest. And now we had to launch the runtime, and this tutorial begin by reusing the app.elf created by. So remember we create this imagine compile getting started.pd. We got a getting started.elf file. Sorry, did you have a question?
No.
Okay. So you just have to locate that ELF file here, and I need to make sure that where is this ELF file. So I need to change this path. Let me see where this ELF file got generated. Imagine.output app.elf. So we will go to imagine.output app.elf, and this is the ELF path. So what you have done is that you have invoked the Python runtime library and called it URT, and then URT Kensington. Kensington is the device code name, and then you get device count. If it says no devices available, it means that either someone is using it or your device is not active. It didn't say anything, so it means that device is good. It will generate accuracy and so on. And we take that ELF path. So how ELF, when you do imagine compile, it creates a directory called imagine.output, and it contains that app.elf file. So if you look here, this is my directory called tutorial notebooks. If you look into imagine.output, it's app.elf. It generates a JSON file, config, and graph. So multiple stages. Then we also have an imagine project which has the individual steps of bank compiler, model compiler, and bank allocator, individual files also. So let's run through this, and this is running on the hardware now, and it will attend the result, and the hardware accuracy is 9804. So remember we predicted that this is how the on-chip accuracy should be. We didn't run it on hardware. We called the untether caller a layer caller, and we asked for, can you give me the estimated on-chip accuracy for quantization-aware retraining? And it predicted 0.984. And now we are at runtime training, and we are running it on hardware right now, and it is giving us the exact same accuracy. So in this case, we learned how you start with an ELF file which gets generated through Untether ML framework, find it in the imagine.output directory, and then provide it to the runtime library using this command, which is load module ELF path and through Untether RT. And then you launch it. And when you launch it, it becomes ready for hardware, and it's loaded on the hardware and starts running. Now, how do you improve runtime performance? You can do network parallelism, you can do replicate layers, you can do data preprocessing, as I talked about in my slides. So in this tutorial, we took the NIST classifier network from the getting started in ML framework and went from the basic Keras model, pre-trained model, to running on the hardware. So that is it for today. For now, and I'm willing to take questions now.
Thank you, Gaurav. Great presentation and great demo. Shows a lot of details on how to get started and play with this software stack. If you have any question, you can unmute yourself and ask Gaurav the question or type it in the chat. So Gaurav, these notebook files, they will be available for people to explore with the board.
Yeah.
And maybe try them. I think it's a great starting point for anyone who want to go a step further in terms
Right.
of subgraphing and adding operators and improving an existing graph. But I think the starting point is pretty good. So you can ask any question when I will maybe jump in the demo and show CMC resources
Okay,
to
that sounds
support
good.
this board. So I'll share my screen. Basically, you can interrupt me anytime and ask question either to Gaurav or to me. So I will bring up the yes.
Yeah, I have one.
Hello.
Okay, thanks, Rob. Can you hear me?
Can you? You are very far from the mic, I think. Can you?
Very hard to hear him.
Yeah.
Maybe can you type your question in the chat if you cannot
Yeah.
get your mic working?
Yeah, it's a good alternative too. Okay, so I think you're gonna type his question in the mic. I don't know who asked the question, but basically this is the parts of the webinar that cover how to get started with the CMC server that has the tsunAImi card. This webpage summarizes the products and services that CMC offer in order to support AI and ML. So researchers can build, optimize, and deploy their applications. Gaurav mentioned that your starting point would be a trained graph that already was trained on GPU, or you just download its pre-trained model. But here in the build section here, we have several platforms that you can use to train a model. So there is the Atlas 800 cluster and the GPU cluster, which has a lot of V100 GPUs. Since we are focusing today on the Untether card, you see here you just click on Untether board and you will have access to the web page of the board. And here you can find high-level details about the board, the use cases, and also you can access the resources. So first of all, I am your first line of support. If you have any question, you can ask me directly via email. But to get started, we can jump to the GitHub that I have created for this board. So this is the getting started on how to access the server. First of all, this is a secure environment, so you need to download CAD Pass from CMC Microsystem. And you log into CAD Pass using your email and password. Then you can access the server by SSH or Jupyter Notebook. So basically, you can obtain the IP address from this interface, and you can SSH to it using your username, and you can start playing with the board either on the SSH or Jupyter Notebook. So I will give you a live demo just how these things work. So we'll bring up my CAD Pass interface. So here, just type your CMC email, password. So once you log in, you will have access to this interface, which show you the AI Jupyter Notebook, which is the Untether AI platform. So you right click, you can have access to the shortcut details, and here you have the IP address of the server you will access to, and also the address of the Jupyter Notebook that will run on the platform. So you can use something like mobile extern, open a local terminal, SSH to your username, And here you can have access to the Untether server. So you see here I have Yasin at Untether. Yasin is my username. And here basically you can check the board status. So the board is installed and is available, and you can start working with it using the script spin up SSH. So let's go and first of all open this file. So this is the file that allow you to launch the Docker container, that allow you to use the board and use the SDK basically. But here I would like to highlight few elements of this file. So first of all, you have here how to map a drive to the container. So in this case, your home directory is directly mounted to the workspace. Here you can pass any AI hardware device configuration from the host to the container. Here you have the port that will be used to run Jupyter Notebook. And here you can have access to like to specify a tag other than the latest. So this is how to play with the Docker container when you want to commit your own version. So let's spin it up. So what we're gonna do, we're gonna launch the container. So when the container is launched, now we are inside the container. Now we can interact with the board. So the system is set up this way. First thing I'm gonna do is to run Untether SMI. This is like NVIDIA SMI. Just show you the status of the board and the different parameters that you can look here. You can also look at the imAIgine version. So Gaurav showed you the versions that are on the portal. Here you can see what version you are using, which links to the documentation. And, you have an idea about what's going on. So Gaurav showed few notebook in action using the board. Here I'm going to show you something on the SSH terminal. So you have some examples already available on this directory, and I'm gonna run one of them. I'm gonna run ResNet 50, and the command is this. I'm gonna just copy it from here. So here I'm gonna run the ResNet 50 demo.py. I'm specifying one chip. I'm gonna just process the first 100 images, and here I provide the path to the images. So here I have a model that is missing, but you can just install it using pip install WebSockets, and then you can run the demo after that. So in some cases, some demos require some specific packages that you can just add by pip install, and this will be installed in the environment. So you see here, it's running on the board. And here you have all the information regarding the steps. So pre-processing, preloading. Here you have the 100 images that are processed in a fraction of a second at a rate of 1,185 images per second. So if you are advanced users and you don't want to use Jupyter Notebook, you can write your code using Python and interact with the environment this way. In the case, if you want to use Jupyter Notebook, you just type this command and it will open a Jupyter Notebook at the port 8080. So once you launch this, you see Jupyter Notebook is launched. And as I showed previously, here, this is the address of the Jupyter Notebook. You just copy it to your browser. And here it will ask you about the token. You can copy it from the SSH window here. And once it's copied, you can start developing using Jupyter Notebook and using the example that Gaurav presented today. So this is like just a demo on how to access the board and how to get started. All the Jupyter Notebook that Gaurav presents today will be available in this section when you log in. But this basically summarized the demo on how to access the board and how to use the resources. So I think we'll have a second chance for questions. So Zhang, sorry, see my mic not working. I am wondering, the QAT is done by pure integer arithmetics only or simulated floating points?
So how would I describe is we perform something like a fake quantization to the weights and activation by quantization and then immediately dequantize them such that we simulate the effects of like rounding during training. The actual computation is performed in the floating point. So I think you are right in that it's done actually in floating point, but we do some sort of like quantize and immediate dequantization. And this is mostly done for performance reasons and is the standard definition of quantization-aware training.
Great. Gaurav, can you provide you research direction? If researchers want to start with the board and want to explore some research opportunity with Untether, what are the main top 3 topics that you think researchers will focus on in order to get some publishable results, I would say?
Right. No, so I think it depends on the use case right now. So for example, if you are working on to computer vision use cases, I think there are plenty of opportunities. I would start with something like a YOLAC tutorial or YOLO Excel, which comes out of box. And then you can come up with different, so for example, one of our customers who is using not the regular RGB images, they're using some satellite imagery and they're trying to publish a paper out of it. So you can come up with a different data set, different use case, and first start with our own YOLO Excel or YOLO model. Obviously, your accuracy will not be good because trained on different model, different data set. But then you can start with retraining, use quantization-aware retraining, and see how it goes. Other approaches, I think my advice would be to look into the processes or the models which you already have, but they are running slower than expected or they're consuming less power, or if you're looking from the green climate change angle also. So your goal should be to like consume less power or like run faster or deployed on a smaller devices. So something that can fit onto a smaller, for example, instead of fitting on a big rack server, how about we fit it on a small chip which TSN 200s or an AI 200s are.
Yeah, thank you. In terms of roadmap, is there any directions at Untether to support more like on-device or edge AI use cases, like on wearable or autonomous cars or?
So we only talked about Run AI 200 today, which is our current generation, which you can purchase right now or acquire right now. And we have a lot of university partners which are acquiring Run AI 200s. But we have also announced our next generation of chips called Speed AI 240, which is it's designed for different use cases. So we realized that a lot of people are looking for NLP use cases and large language models. So we decided to focus more on a chip which does all of that. So we come up with Speed AI 240. It's 7 nanometer Gen PCI Gen 5 x64. It's faster. The only catch is that it is still bigger. So Run AI 200 is like this big chip. And Speed AI 240 is like this big. But we are working with our customers who are coming from the auto industry and they want smaller chips. So they want like half size of Speed AI 240 or even one fourth. So that is in our roadmap, but that will come out next year when we have engineering samples. So we'll have, right now we are calling our Speed AI 240 B4 internally, and then we have something called B3, which is smaller than B4, and then B2, which is for auto grade, and B1 is like for smallest edge cases or wearable. But for that, you'll have to wait till next year.
Yeah. Right. Any questions from any additional questions from the chat? I think since the webinar will be posted afterward, it will be accessible to everyone, and you can either interact with me directly, and then we can involve Gaurav for more like technical questions. And with that, I would like to thank you for your presentation today. Oh, we have a last chance for a question.
Yeah.
Go ahead.
Hello.
Go ahead, Shahab.
Okay. Thank you for your great presentations. I just have a question about the power consumption. Does this, when we're running, does it give some information regarding the power consumptions of the, for example, the 100 image processing? Can we access through the network, or for comparing with the GPU or other, edge device platforms?
Right, yeah. So yes, you can compare the power numbers. And so for example, Yassine has showed you Untether SMI. We have similar tools which you can type in and generate the current power status. We are working on some other tools also which will give you which will generate you reports on like the whole thing, how much power consumption, average power consumption, maximum and minimum. So that will be made available pretty soon. But for now, you can get the real time, like what's the power consumption right now using our tool set.
Okay, thank you so much.
Okay. Okay, thank you everyone. Thank you, Gaurav, for your great presentation today. Very insightful, and I hope we will get more use cases to the board and more feedback to you. And with that, I will conclude this webinar. So thank you for attending today, and have a nice day.
Thank you.
Bye-bye.
Thanks for the opportunity. Bye.
Bye.